Good morning, everybody. Hi. Today we're going to do all of differential calculus in 75 minutes. All right. So, welcome back to class. We're going to go very, very quickly today. If you've already taken a course in calculus, this will be a lot of review, and it should be very beneficial to you. If you've never seen calculus before, I think you're going to be surprised at just how easy calculus is. Much easier than pre-calculus. So, let's begin. In geometry, you consider the following situation. You have 2 points on a plane, and you connect them with something approximating a line. And what Euclid tells us is that if you put down 2 points in a plane, there is only one line that goes through. Right? Try to find another line that goes through these 2 points. Right? Can't do it. But if I have 1 point, and I say, okay, now draw the line through that point. Can I do the line? No, right? Because I can draw this line, I could draw this line, I could draw this line. In fact, how many lines can I draw through that 1 point? Infinitely many, right? There's just no limit. All right? So, calculus is somehow a way to get around this problem. Calculus is going to start by looking at 1 point and drawing a unique line through this point. Now, of course, we just saw you can't do that. All right, so what in the world can you do? Well, here you need 2 points. Calculus is going to look at the following situation. I take a curve, and I pick 1 point on that curve. And I want to draw a unique line going through that point. So in this case, right, I have 2 points, that's how I do it. Calculus would say I don't have some second point off this curve, I just have the point, but I do have this curve. And I'm going to draw a unique line. And it's going to be called the tangent line. Okay, so how do we do it? Well, we do it with a very clever idea. We're going to approximate. So where does this come from? Well, let's say you're driving down the street, or maybe a little longer, maybe you're going to drive across the country. And every so often you mark how long it took you to get from point A to point B to point C to point D. Well, you can figure out, if you take, okay, let's see, how far was it, and I divide it by how long it took me, I can figure out my average speed from point to point. Okay? But how would you actually find your instantaneous speed at some point? Well, there's a very simple explanation. You don't even need calculus for it. You just look down at your speedometer. Right? And that tells you how fast you're going in your car. Okay. But let's say you didn't have a speedometer. How do we do it? Well, here's how we do it. Okay, again, we're going to draw a curve. We're going to pick a point on the curve. And, well, since this is math, let me add some axes. And I'll call this the x-axis. And maybe this is the y-axis. And I'll give a name to this curve. I'll say it's some function of x. Okay? And so this point here has a coordinate. What's the coordinate? The coordinate is x, f. F of x, right? So that's x, and the height is f of x. That's the coordinate of the point. All right, now, I want to know the speed at this point. Say if this was your position function. Right? I want to know this velocity at this point. So instead, I draw another point, and I draw a line going through these 2 points. Okay, and now this is some other point on the x-axis. Let me call it, well, I could give it a totally different name, but instead what I want to do is say, well, it's x plus some number. Right? It's just this distance. That's h. And of course, then the y-coordinate, right, is just f of x plus h. Okay. Now I have a line going through these points. This is called a secant line. Secant because it's hitting in 2 spots. And I can compute the slope of this line. So slope of the secant line is what? Well, you just need to know how you find the slope of a line. Right? Well, okay, we take the second point and we're going to subtract the first point. All right, what do I mean by subtract the first point? I mean I'm doing rise over run, right, from this point down to this point. So how much did it go up? Right? Well, that's just this distance. That's the rise. So it's f of x plus h minus f of x, right? y2 minus y1. Divided by the run. That's how far I went this way. Well, that's going to be x plus h minus x. And of course, that's just this distance, which is h. No problem. Okay? So I get a line, and I have the slope of it as given by this, which is sometimes called a difference quotient. Okay, now why do I care about the slope of this line? Well, if you take a position function, draw 2 points on it, draw this secant line, and ask what's the slope, what is that actually telling you? That's telling you the average velocity between this point and this point. Right? Because what does it mean to do the average velocity? It's just saying, okay, how far did you go, right? That's the y, and how long did it take you? Take the time it took you, how far you went, divided by the time it took you. Right? That's exactly what this is. It's the distance you went divided by how long it took you. Okay, so now we know that this is giving us the average velocity between these 2 points. Okay, well, let's say we took this point and made it closer to our original point. Draw my nice curve, put in my point x, and now I'm going to put this point a lot closer. Right? Because, if I put this point way away, then that average velocity doesn't really tell me a whole lot about the instantaneous velocity. But if I put this point closer, then the average velocity is going to be closer to the instantaneous velocity. So I take this point, move it a lot closer, and again I can draw the secant line. All right? I can compute this same quotient, except now I'll be closer to the actual answer. Okay? And then I can do it again, except now I'm going to put them right on top of each other almost. And I draw the line that goes through those 2 points. And you can see what's happening is up here you have the line going like this. As you get a little closer, it starts to tilt up a little more. Right? Now it's tilting, but the amount that it's tilting as you get these points closer is just a little bit. And it's getting closer and closer to some specific line. Right? And eventually, let me put it here, I'm going to end up with 1 point, and the other point's going to be so close that you can't even see it, and I'm going to have a line which hits it at 1 point. And that's going to be called the tangent line. So this here is a secant line, and this here is a tangent line. Okay, now, how do I get back to this formula and write something mathematical? All right, well, one of the things we're going to do in this class is examine this process of getting things really, 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 really close. And the way we're going to denote it is by LIM, which stands for limit. Right? And I'll put something at the bottom here. I'm going to take this difference quotient, which is the slope, and I'm going to look at what happens as h, right, which is the time interval I'm looking at, gets really, really tiny. And the way I'm going to write that is by writing h goes to 0. Right? Now, a very good observation at this point is, what if I chose my h to be negative? What if it was on the other side? And so this notation is supposed to mean that h can go to 0 both from this side and from this side. And if we want to do just one side or the other, we're going to have some more notation for that. This here is called the derivative f of x. And I say if it exists. Because what we're going to see in this class is that there's going to be some times where this process of building a tangent line from approximating with secant lines is not going to work. In most of the nice cases, everything's going to be fine. But there will be cases where it just does not work. And so we always have to have this little proviso, if it exists. Let me give you a little notation. There's going to be tons of notation for the derivative. Okay, so the derivative of f of x, I should say at a point x, for instance, could be a, whatever you like, is denoted by, okay, so first, f, we say f prime of x, right? Just put a little dash up there. Right. Another way you might write it is the derivative of f of x. And then sometimes you write dx of f of x, or if you don't care about what point you're starting with, dx of x. Okay. We will mostly use the first two, but you will see this sometimes in books, so I want you to be aware of it. Okay, so let's do an example. A real example. Well, let's start with a stupid example. Because stupid examples mean you already know the answer. Let's say, let's change it so that it really matches the idea of something moving. I'm going to change the whole name of the function. I'm going to call it my function s, which is going to stand for position, which doesn't make any sense to me, but that's what the physicists do, right? And t stands for time, which does make sense to me. Okay, so this is a position function. Okay, fine. I want to write down a function which says that over time, I'm always traveling 3 times what time it is. All right, so I'm getting faster and faster. So at 1 second, I'm traveling 3 whatever per hour. If it's been 10 seconds, I'm traveling 30 whatever per hour. So what would be a good function for that? 3t, very good. Okay, so this is really stupid, right? Okay. So at any point, you know what your velocity is. It's just 3 times the time. Okay. Okay, so let's see. I'm sorry. Let's backtrack a second. Okay, what we've done here is not 3t. I can't listen. Okay, so we actually want the velocity. What I just said is we want the velocity, which I'll write as v, to be 3t. All right. So this is a bad example because I wrote this backwards. What I actually want is for my velocity to always be 3. This is what I want. Okay, I'm sorry. Okay, so what would my position function be if I always want my velocity to be 3? 3t. 3t. That's the answer is actually correct, but what I said was incorrect. Okay, so I want my position function to be 3t, meaning that at any given time I'm going exactly 3 miles an hour, or whatever. Okay? So if I take the derivative, which is supposed to tell you the instantaneous velocity, I should get 3. Right? That's what I'm expecting to get, is 3. Okay, so let's just try it. I'm supposed to do the limit as h goes to 0 of, okay, the function, which is 3t, applied to x plus h, right? Or in this case, t plus h. Okay, so what happens if I replace t by t plus h? I get 3 times t plus h. Okay, the next half is a minus, then the function, which is 3t. And then I divide by h. This is what I need to compute for the derivative. Right? So this is equal to s prime of t. Okay. Well, let's simplify this a little bit. Because you look at it and say, oh, I can simplify that. Okay, so let's look at 3t plus h minus 3t over h. Okay, so on the top I get a 3t and a minus 3t. Okay, those just cancel away. Perfect. And then I get a 3h. Okay. Now, one of the important things is, in the end, when we take the limit as h goes to 0, we never let h actually be 0. Because if you did, you can't divide by 0, right? We only care about h as it gets really, 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 really tiny. Okay? So we never, ever, 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 ever let h equal 0. Which means we can cancel. Right? If this was a 0, bad, 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 bad. So we just get 3. Okay, so this limit is equal to the limit as h goes to 0 of, well, this thing we just computed was 3. And of course, as h goes to 0, this is always 3. Perfect. That's exactly what we expected. So what this verifies, at least in this special case, is that velocity is the first derivative of position. So velocity is the derivative of position. Okay. Now, another way to think about this is to say, okay, so this is somehow how much position is changing with respect to time. So velocity is how much your position is changing with respect to time. Okay, duh, right? That makes perfect sense. Velocity is how fast you're going. It's how much you're moving over some time interval. Okay, no problem. Well, let's just think. Velocity can change too, right? Right? As I run around the room, I stop, I start, I run. My velocity changes that whole time. So you could ask again, how does my velocity change with respect to time? And what do you call that when your velocity is changing?
Acceleration.
Acceleration, right? If I start here, I'm accelerating, and I'm decelerating when I stop. Right? So if you want to find the acceleration function, what should you use? The derivative. So acceleration is the derivative of velocity. So if you've never seen this before, you might already get the idea. This might be important if, for instance, you wanted to build a rocket that went somewhere. All right? If you want to know how fast you need to accelerate to do something, or what velocity, or where the darn thing is going to be when you do the ohms burn, you might need to know how to compute a derivative. Okay, so let's do another example. Let's do one not so stupid, right? I mean, this is so easy. You know ahead of time what the answer should be. Let's say my position is given by the square of time. Right? So let's just graph that. And we don't have to restrict ourselves to time equal to 0, but let's just do that for now. Right? Looks like this. Of course, if we allow negative time, right, we'd complete it like this. You have a parabola. That's what the graph of t squared looks like. Okay, now, whereas this one was really easy. What does the graph of this look like? Well, it's just a straight line going up. If you want to draw the tangent line, well, it's just the darn line itself. Right? Because that exactly is the approximating line. But this one, this is not so trivial. Right? I mean, if I pick a point here, and I draw the tangent line, it shouldn't be at all obvious what the slope is. What should be obvious is that as you go up, right, or out if you like, that this line is going to get steeper and steeper. Okay, whatever the tangent line here, right, that's definitely a steeper line. The slope is greater. So whatever our answer is, it should somehow account for that. Okay, so let's compute it. So we need to compute the limit. So s prime of t is the limit as h goes to 0 of, okay, we have to do the function applied at t plus h. So the function is t squared. So that means I need to do t plus h squared. Then I need to subtract the function and divide by h. Okay, we have exponentiation in there. We're going to have to play around with it a little bit. Let's see what's going on. So let's forget about the limit for now and just fiddle with this thing. So I have t plus h squared minus t squared over h. All right, so this, of course, in this class, you already know how to expand a binomial. So I assume you can do this. I do it very quickly for you. This is t squared plus 2th plus h squared. All right, that's this piece. And then I subtract t squared. And I have to divide by h. Okay, let's see. I have a t squared on the one end and a minus t squared on the other. Gone. And then I just get 2th plus h squared over h. Ah, but look, I have an h in both terms. Factor that bad boy out. Divide by the h. Why can I divide by the h? Because h is never 0. So when I divide by the h everywhere, I get 2t plus h. Okay, and that's as much as I can simplify this. So let's plug it back into the limit. So I get the limit as h goes to 0 of 2t plus h. Okay, so I have some function, 2t plus h, and I'm looking at what that function does as h gets really, really small. What does this function get really, really close to?
0.
Well, h goes to 0. It goes to 2t. So this tells us that at any given point on this curve, the velocity is 2 times the time. Now, if you ask, what was that thing I said about this one, where I said it incorrectly, right? I was saying I wanted something where it would be 3 times the time, right? In this example, and of course then I said, well, that's not really what I want. And then you all laughed at me for being stupid. I thank you very much for that. Okay? Well, this is pretty darn close, all right? And so we will see how to get one that's exactly 3t. Right, but this one is 2t. So this says if you're at 1 second, you're going 2 miles an hour. If you're at 20 seconds, you're at 400 miles an hour. If you're at 99 seconds, you're at 9,801 miles an hour. No, that's not right. I squared everything. Okay. Okay, so we've now computed the derivative of 3t and of t squared. There are a lot more functions to compute derivatives of. I can't do them all in 75 minutes. So instead what I do is just give you the rules. Right? What we're going to do in this class is prove rules which make it so that we don't have to go through this whole limit formula every single time. Because this is kind of a pain. And you can imagine if I put a 3 up here, what's going to happen? I'm going to have to expand a binomial cube. So I'm going to have to start whipping out Pascal's triangle and remembering all these things. If I put a 4 up here, you just tune me out and just forget it. I'm not, no, check please. So we better come up with some general ways of attacking these functions. Moreover, all I've given you so far are very simple polynomials. There's all sorts of functions out there that aren't polynomials. Whew, lots to talk about. So I had to take pre-calculus where they taught you all those trigonometries and exponential functions and how to graph stuff, all preparing you for this class. So that when I talk about sine and cosine, go behind that. Okay, so what can we do? Well, I'm going to give you a bunch of rules. First, the power rule, then the sum rule, and the product rule, the quotient rule, And then the one that gives everybody fits, the chain rule. All right? So, the power rule is very special because it really has to do with polynomials. Right? But all these other ones, these are going to apply pretty much everywhere. So these are the things you're going to have to know in this class. So let's see how the power rule works. Right? Well, this looks at a very specific kind of function. It's going to look like x to some power. Normally they put n up there. And n usually stands for a natural number. But it's going to turn out that you can put any real number up here. It could be pi, could be 2, could be negative 46. Could be your social security number, doesn't matter. Well, no dashes. You have to take the dashes out. Okay. And let's say I want to compute the derivative. Okay, notice depending on how the problem is stated, I switch between the notations. Right? If I told you f of x equals x to the r, then I would write f prime of x. But if I just want to write the function, I write d dx. Right? This just means take the derivative. Okay. Now, I'm not going to go through the process of going through the limit. I'm just going to tell you how to do it today. That's what the whole course is for. Actually, prove it. All you do is you take this exponent, you bring it down, you multiply it by x raised to the same exponent, but subtracting 1 from it. It's so easy. Right? So for example, the derivative of x squared is, well, let's see, I take the 2, I put it down, I put the x, and then I raise it to the 2 minus 1, which is 1, which of course we never write the 1. You get 2x, which is what we got here when we took the derivative of t squared, right? We got 2t. That's what you expect. Okay. If I have the derivative of x to the pi, then the derivative would be pi x to the pi minus 1. Okay. Easy enough. Let's look at a special case. What if I had 4? No, let's just do 1. Let's just do 1. That matches what we've done. Okay, well, how does that fit into this rule? How can I write 1 as a power of x? X to the 0, yeah? Okay, so this is going to be, well, I'm supposed to take the exponent, which is 0, and put it in the front. And then I put x to the minus 1. Okay, well, it doesn't really matter what I get over here, does it? Because I multiplied by 0. So it's just 0. Okay, so what does this tell me? This says that if I have a function which is constant, okay, so think position function. What does it mean to have a constant position function?
It's not moving.
It's not moving, right? What's its velocity if it's not moving? 0. Okay, that's exactly what you'd expect to get. Good. It matches reality. Excellent. Okay, so this power rule, very useful when you got polynomials lying around and you need to use it. And in conjunction with the chain rule, we're going to be able to use it for a whole lot more even than polynomials. Okay, what about the sum rule? Well, the sum rule is what happens when you start adding together functions. Okay, for instance, I might have a function f of x, and I might have another function g of x added together, and I want to know what's the derivative of this sum. For instance, x squared plus x. That's a sum of two functions, x squared and x. How do I get the derivative? Well, it is exactly what you would want it to be. The derivative of a sum is the sum of the derivatives. It's just the derivative of f of x plus the derivative of g of x. It's exactly what you want it to be. Okay. So for example, if you have the derivative of x squared plus 1, what is this going to be? Well, it's the derivative of x squared, which we computed to be 2x, plus the derivative of 1, which we computed to be 0. So it's again just 2x. Okay, but now look what we found out. If you took the derivative of x squared, you got 2x. If you took the derivative of x squared plus 1, you got 2x. That's kind of weird. Why would that be? Well, let's see, what's x squared? X squared is this nice parabola. X squared plus 1 is the same parabola, but you shift it up by 1. Of course, shifting it, only you know you did that, right? The parabola looks the same. You draw tangent lines, they look exactly the same. Right? Another way to put it is, it's like starting at a different place. Right? Where you started driving doesn't matter as how far fast you're driving right now. Right? As long as you follow the same position function. Okay, so this sum rule is going to be very, very useful. A pseudo-corollary to this sum rule, which I put down at the bottom, is the following. Let's say I have a function, and I multiply it by a constant. For instance, I have a function x. I multiply it by 2. I get 2x. Okay? That's a function multiplied by a constant. By a constant, I mean a number. Okay? And what's the derivative? Well, it's exactly what you would hope it would be. You just take this constant and move it out. Just forget about it. And then multiply by the derivative of f of x. So if I wanted to know the derivative of 2x squared, 4x, I just take that 2, pull it to the front, forget about it for now. Say the derivative of x squared is 2x, and now bring that 2 back in, and I get 4x. Okay? What about the product rule? The product rule says what happens if you multiply two functions. Okay, this is where it is not what you expect. In the history of calculus classes, the most common mistake made is to think that the derivative of a product is the product of the derivatives. It's not. Don't do it. It's more complicated. It's not very complicated, but it's more complicated. The formula is you take f of x and multiply it by the derivative of g of x. Then you add g of x multiplied by the derivative of f of x. All right? So you're always going to have two terms. One of them is the original function times the derivative of the other, and the other is the other function by the derivative of the other. Okay? And of course, it doesn't matter. You don't have to memorize what order this comes in because it's addition. Addition, you don't care. It's commutative, as we say in the biz. Okay? All right, so let's do an example. Let's say I do the derivative of x squared times x cubed. Okay, now we all should know what the answer is already. Right? X squared times x cubed is x to the fifth. The power rule tells us how to do that. It's just going to be 5x to the fourth. That's what the answer should be. Well, let's see what happens. So we're supposed to do, okay, the first function, x squared, times the derivative of x cubed. All right, okay, that's 3x squared. Plus, okay, the second function, x cubed, times the derivative of x squared, which we all know now is 2x. Okay, so let's see. I get x squared times 3x squared. That's 3x to the fourth. And x cubed times 2x. That's 2x to the fourth. So 3x to the fourth plus 2x to the fourth, 5x to the fourth. That's exactly what we want. And this example, of course, immediately shows you why the derivative of the product is not the product of the derivatives, because it doesn't give you the right answer. Right? If you just took the product of the derivatives, you'd get 2x times 3x squared. That's a cube. That's not even the right power of x. So you really have to use this formula. Okay, what about the quotient rule? Okay, so quotient means divide. So this is when you take a function f of x and you divide it by a function g of x. Imagine if you wanted to take sine of x divided by x squared. Right? That's a quotient of two functions. Okay, now this is not the one that causes people to make a lot of mistakes on exams. This is just the one that nobody can remember. They just leave it blank. Okay, so there's a mnemonic for this, which I use to help me. I say, low D high, less high D low, E-I-E-I-O. Okay, and the reason why I do that is because the formula is going to look like this. Okay, you do g of x times the derivative of f of x. Oh boy, I'm going to run out of space here. Okay, chain rule, you're getting bumped. Minus f of x times the derivative of g of x divided by the square of g of x. Okay, this is nasty. This looks really bad. Now there's one saving grace. A quotient is actually, just forget the derivative, this is actually f of x times g of x raised to the minus 1. So if you want, you can always use the power rule and the chain rule and the product rule. You don't need to know the quotient, but it's faster just to memorize this. Okay, and so my little poem is, okay, the g of x squared, I don't have a problem remembering this, but if you do, I can tell you a longer version of the poem. Okay, but I think low d high less high d low. Okay, low low d high less high d low. E-I-E-I-O. Because I have kids. Okay, so this is the formula. So we do an example. All right, let's do the derivative of x squared plus 1 divided by x cubed. Okay, so this says I have to do low times d high, the derivative of x squared plus 1. Ah, we know that one. Derivative of x squared plus 1 is 2x. Okay. Minus. Now, the reason why you have to sing the song and get in the right order is because of this minus. All right? Minus is not like plus. Plus, you can do it any way you want. Minus, and. So we got to do it in the right order. Now we do high d low. So high is x squared plus 1. Low is x cubed. And then we divide by the square of the denominator. So I take x cubed and I square it. What's x cubed squared?
6.
X to the 6th. Very good. That was a trick. Some people say x to the 5th. That's incorrect, of course. But then I laugh and make fun of you. Okay, we'll have to move this chain. Okay, so let's just simplify it a little bit because I can't let a poor thing like this be unsimplified. Okay, so let's see. So we get 2x to the 4th minus x to the 5th minus x cubed divided by x to the 6th. All right, and let's see. Each of these terms has at least an x cubed in it, and there's an x to the 6th on the bottom, so I can cancel an x cubed. So I get 2x minus x squared minus 1 divided by x cubed, which we could rewrite if we wanted to, but I don't. Okay? So the quotient rule is very efficient for tackling this sort of a problem. Right? Now, let's step back for a second and remember what the derivative was good for. You have some position function. You draw the tangent line at some point that tells you the instantaneous velocity at that point. Now, imagine what this function looks like.
Don't you have the 3x squared?
Did I mess up?
3x squared, not x squared.
Oh, where am I talking?
Right there.
Right here?
It's supposed to be 3x squared.
Oh, did I just copy x cubed?
Yeah. From the
Very good, very good, very good. Okay, so we get 3x squared. So now we just have to fix this. So that became minus 3x to the 4th. Minus 3x to the 4th, and then minus 3x squared. Okay, so now, this is even better. Because look, 2 minus 3x to the 4th. So that's going to be minus one of them, and then we can at least get rid of a square. So we get minus x squared minus 3, and then we get rid of 2 of these, so x to the 4th. So it's even simpler. That's great. Thank you very much. Okay, so again, though, if you had this function, at some point we're going to learn how to graph this really quickly. But assuming you didn't know how to graph it at this point, you didn't have your calculator lying around, you'd say, I have no idea what the instantaneous velocity of this function is when x equals 3. How could you know, right? It's some nasty thing. Okay, this tells you. Just plug in x equals 3, boom, you know the instantaneous velocity. Okay. Now imagine Isaac Newton sitting around, 400 plus years ago, trying to figure out, the path of planets orbiting around the sun. And he's trying to figure out gravity, right? And he's trying to figure out how everything works. And all of that, everything he's basing it on is, I need to know how fast things are traveling. All right? He's the one who cooked all this stuff up. Can you imagine how important this was for him? When he finally figured out, boy, some really weird, complicated functions, I can immediately figure out how fast they're going using just these simple rules. Right? And that's why he threw that apple on his head. He was so excited. Okay, so one more rule. This is usually considered the hardest one. This is called the chain rule. All right, so how does it work? Well, it's going to look awfully darn complicated. So let's say I have a function f, and the input is another function, right? It's called a composition of functions. Okay, now, before I always told you the rule and then I give you an example. This one I have to give you an example right to start. Okay. How about x plus 2 squared? This is a composition of functions. Right? In this one, f of x would be the function x squared. And g of x would be the function x plus 2. Right? You've started with x plus 2, and then you've squared it. Okay? You've composed two functions. So that's what I mean by this. Right? It looks a little weird, because here the f's on the left, and here the 2 is up high. Right? But more examples of this would be like sine of 2x. Okay? Here, f of x would be the sine function, and g of x would be the function 2x. Okay? This is what a composition of functions looks like. And if you have that, the derivative is going to be, you do the derivative of f prime, the derivative of f, you get f prime, and you again apply it to g of x. And then you multiply by the derivative of g. Okay? All right, so this one we don't know sine yet, but let's do the derivative of x plus 2 squared. Okay, this formula says you take the outside function, the f, which is x squared, and you take the derivative. So we need to know the derivative of x squared. We know it's 2x. But we don't just say 2x. We have to apply it to g of x, which is x plus 2. So instead of 2x, we get 2x plus 2. Thank you very much. I like participation. Find a candy bar, you'd get one. I'll bring candy. That'll be good. I like candy. Okay, so we do 2x plus 2. But then we have to multiply by the derivative of this inside function. Okay, now the derivative of the inside function, we have x plus 2. Okay, to find the derivative of a sum, right, because that's what we have, x plus means sum, we have to use the sum rule. So first we have to do the derivative of x. Okay, well that's 1x to the 1, right? Okay, bring the 1 down, you get 1x to the 0, so you just get 1. Okay, so the derivative of the x part is 1, and the derivative of 2, it's going to be 0, right? Because what is 2? It's just a constant function, right? It says you're not going anywhere. The velocity is 0. So you just multiply by 1, okay, which does nothing. So we just get 2x plus 2, or 2x plus 4. Okay. Using these rules, you can do you can find the derivative of any rational function at this point. Rational function is when you do a polynomial and you divide it by another polynomial. All right, so it could be just a polynomial, 2x cubed. It could be 1 over x. It could be 3x to the 400th power minus 16x plus 4 divided by x squared minus 6. Right? You could also do functions which weren't rational functions because they weren't polynomials, things where you had real numbers as exponents. Okay? But there's more. There's more, right? Why is there more? Because there are more functions. We had functions we saw here like sine. Right? There's cosine, there's exponential functions, there's logarithms, inverse functions, hyperbolic functions. Oh yes, there's more. Okay, so let's see what we can say about those more. Well, If you didn't think sine and cosine were related enough, I'll just tell you something. The derivative of sine is cosine. Now that's cool. What does that mean? Let's say I try to graph the sine function. Okay, I won't draw all of it because it takes a long time. Okay, so this is what the sine function is looking like. If I compute the derivative, that means I pick a point, for instance. I draw a tangent line. What's the slope of this line? Well, it is not obvious to me, at least a priori, that the slope of this line should be, well, take this angle, whatever it is, theta, and just look at cosine of theta, and that tells you what the angle is. And that's really weird. What it also tells you is, well, if you take sine and cosine, what do you know about the values of those take lines? I mean, what's the highest point it's going to be? 1. And lowest point is, of course, minus 1. This tells you that the slope of those lines that you get, since they're always a function of cosine, they're always going to, the slopes are always going to be between 1 and minus 1, which means the slope of the sine can never get too much or too little, right? It can't be 2, for instance. None of these lines can have slope 2. So that's kind of cool. Right? Okay, well now you know sine. What about cosine? Well, in a perfect world, this would be sine of x, right? Not in a perfect world. You put a minus in. But that's not so bad, right? It's a little minus. It's just the opposite. All right, and so there's a little chart that I like to keep around. I don't use it myself, but people have had success with it. Okay, the D stands for differentiation. The reason why I put this in is because this chart becomes useful in Math 166 as well when we do anti-differentiation. And D means you go down also. So the derivative of sine is cosine. Derivative of cosine is minus sine. Now we can find the derivative of minus sine because we saw if you had constants like minus 1, you can pull them out. So all you need to know is what's the derivative of sine. Well, it's cosine. Then you got to put the minus back. So the derivative of minus sine is minus cosine. And what happens when you get to minus cosine? Well, again, you can pull the minus out. You say the derivative of cosine is minus sine, and then I put the minus in, and I get plus sine. So I go back up to the top. Right? So if I want to know my derivatives, all these sines and cosines, I just go down this, and if I ever get to the bottom, back up to the top. Okay. I won't give you all the trig ones today, but I'll give you one more, because you can get the rest of them from what I've given you. Okay, now this one's kind of strange. Derivative of the tangent function, right? Which remember, what's the tangent function? It's sine over cosine. So I can compute it using which rule? The quotient rule, because it's a quotient. So this is the derivative sine over cosine. Okay, let's compute it over here. Oh, well, actually, let me not erase it. Oh, I erased it. Okay, so this is equal to, it says I have to do low d high less high d low. E-I-E-I-O. You can't not do the last bit. Okay, so I do low cosine, d high. So the derivative of sine, which is cosine. So it's just cosine squared. Okay, less, which means minus. Okay, high, sine. D low, the derivative of cosine, minus sine. And I don't mean the minus sign, I mean minus sine of x, as opposed to the plus sign. Not sine, S-I-N, I mean S-I-G-N, but not that. Okay, so I have to do, let's see, minus sine, so it's going to square it and put a plus here. Okay, divided by the square of cosine. And I can simplify this. Look at this top. That should. What is cosine squared plus sine squared?
1.
1. Excellent. So this is just 1 over cosine squared. Right? Now 1 over cosine, right? That's the reciprocal of cosine. What is that?
Secant.
That's secant. All right. Of course, if you square it, you get secant squared.
We're leaving off the sine too.
What's that?
Squared.
Did I leave something out?
What happened to the sine squared?
So this is this. Oh, so cosine squared plus sine squared x equals 1. All right. So this is one of those trig formulas you got to remember. All right. You go back and do your algebra trig review. All right. So big one. Sine squared plus cosine squared equals 1. This is also going to be cool next term when I show you a really cool integral trick using this formula. But that's a while from now. Okay, so we computed that the derivative of tangent is secant squared. Okay, now that's, who would have guessed that? I mean, maybe if you were thinking, what's the derivative of sine? And you were, kind of caught dreaming. You think, cosine, no problem, right? You could have guessed that. Nobody in a million years would say, oh, derivative of tangent. It's probably square secant. Not going to happen, right? So this is really something surprising. And of course, the really nice thing is all the other trig functions are built from sine and cosine. Right? Cotangent is just cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. Right? And so you can find all of them just using the quotient rule. And if you do that, write out a little table, you're going to notice a lot of patterns. It's usually going to be the cases that s's turn into c's, right? So like sines turn into cosines. Right? So whenever you have s's, they're going to turn into c's, and usually they'll pick up a negative sign when you do that. Right? But you have to see where they do. Okay? So now we can do some tricks. So now we can actually compute this derivative, right, of sine of 2x. Let's do that. All right, so the derivative sine of 2x. All right, well, it's a composition of two functions, sine of x and 2x. So we have to use the chain rule. I would have called it the composition rule, but they call it the chain rule. What does the chain rule say? It says I have to take the outside function, which is sine of x, find its derivative, it's cosine of x. Then apply it to the inside function, which is 2x. So I get cosine of 2x, and then I multiply it by the derivative of the inside function. Right? So I need the derivative of 2x, which is 2, right? Why is it 2? Well, the 2 you don't worry about. This is a constant. You pull it out. You say, what's the derivative of x? Well, you bring the 1 down. You get 1x to the 0. Right? That's just 1. Then bring the 2 back in. You get 2. So we just put a 2, which I'll move to the front. Oops. Don't want to kill my C. Okay. And so there's the derivative, 2 cosine of 2x. Sweet. And if you think about it, using these rules that we put on, we can throw all sorts of crap in there. You could do sine of the quantity x plus 3 squared divided by tangent of 2x plus 4, and you use all sorts of nastiness. I can make these problems as hard as I want to, and all you have to do is break them down by the rules and apply it one step at a time. Piece of cake. Okay. Okay, so we have some trig functions. Let's do some other functions. How about exponential functions? This is where it gets really neat to me. This is cool. So remember, exponential functions. This is where instead of having a variable raised to a constant power, you have a constant raised to a variable power. So for instance, 2 to the x. That's an exponential function. Or in general, a to the x, where a is a constant. Okay, so what's the derivative? Well, I tell you what it is. The derivative of a to the x. Of course, we always have to be a little careful with what constants we're putting in here. So just for, well, probably with logarithms it's more important. But let me just keep a greater than 0 for now, just so I don't run into any problems with it. So what is my derivative going to be? Well, it's really cool. You just write down a to the x again. And this will almost be right already. It's just off by a little bit. It's off by the natural logarithm of a. Okay, so remember ln, this is the logarithm base e, which you should have seen in pre-calculus. Okay, so this is really nice. This is, you draw an exponential function, right, which usually looks like this. Right? So it's going to tail off to 0. And you want to know how fast you're going on it. Well, at any given point, so if that's, so this is a to the x. So if this is point t, right, then this is, excuse me, a to the t. The speed is just a to the t times whatever the natural log of a is. Right, so it's just a little bit more than a to the t. Okay. And let's look at a very special case. What if I do the derivative of e to the x? Right? So here e is the base of the natural logarithm, 2.71828459045, and so on, right? Well, the derivative is e to the x times the natural log of e. Right? Well, when you do a log base something of that something, what do you get? You get 1, right? Because that's really asking, what do I have to raise e to get e? Well, of course, you have to raise it to the first power. So this is just 1. So the derivative of e to the x is e to the x. This is great. This is so awesome. It is the only function which is its own derivative. That's really cool. Which also means, okay, first, if somehow we're traveling on a position function, which was e to the x, and you said, how fast am I going at any given point? Right? Well, again, it's just given by e to the x. You say, what's my acceleration at any given point? Well, acceleration, remember, that was the derivative of velocity. Of course, the velocity was just the derivative, e to the x. The derivative is, again, e to the x. So the acceleration is always e to the x. Now, the third derivative, anybody know what that's called? Right? You take how fast acceleration is changing. People don't normally think about that. Right? But if I'm accelerating, and I'm really accelerating, right? What happened there? Well, there was a jerk forward, right? And that's what the physicists call it. They call it the jerk. So the derivative of acceleration is the jerk, which is why I used to call my brother the third derivative. Okay, so e to the x, very special. Okay, now we can couple these all together. We might try some really nasty problem. How about the derivative of e to the sine of x squared? Okay, this is a lot of garbage in here. Okay. So this is a real chain rule problem because I have a function e and I'm applying it to a function sine. But again, sine of x squared, so which really means I have another chain rule problem. I have to do the derivative of sine of another function x squared. So I'm going to have to apply the chain rule multiple times here. So the chain rule says you do the derivative of the outside function. Okay, but the derivative of e to the x is e to the x. It doesn't change anything. And then you apply it to this function. So I just write the same thing down. Okay? But I don't stop, which is what some people do on tests, but you don't, because you still have to multiply by the derivative of this inside function. Okay, fine. I copy this. It's done. Now I need the derivative of the sine of x squared. It's, again, a chain rule problem. So I have to do the derivative of sine, which is cosine, applied to the inside function. So cosine of x squared times the derivative of the inside function, x squared. Of course, the derivative of x squared is 2x. So I can put a 2x. And if I want to rewrite it, I get 2x e to the sine of x squared cosine of x squared. Whew! Not so hard, but, you know, not easy. And again, if somebody showed you this function and said, what is the velocity at any given point? How do you come up with that? Right? Very, very tricky. Okay, what do we got? Okay, we have just enough time to talk about applications. All right, so the theme, of course, here is starting with some position function and finding the velocity at a given point. But calculus is good for so much more. So much more. Right? The most common application of calculus is what are called optimization problems. And how do I optimize? What do I mean by that? Well, let's say, for instance, I was a business person and I was selling a product. If I'm selling a product, I might be able to graph down how much I'm going to sell based on what price I sell it for. So let's say if I choose my price, I can tell you what quantity I'm going to get. And of course, well, actually, what I really should say is let me write it like this. I don't want to. Because the truth is, you're not really trying to maximize your quantity, are you? You're really trying to maximize your profits as a business person. Okay? So what I really want is, if I know my price, let me say this. If I know my quantity is a function of price, okay? So I know somehow if I sell it for $2, I'm going to sell this many. If I sell it for $3, I'm going to sell this many. I can then figure out what my profit is, because I know how much it will cost me to make all these things. So let me put my profit, sometimes it's written as pi. And I have something like this. It's very simple. So, of course, where do you want to produce? Well, clearly, that's where you want to produce, right? That's where profit is maximized. Okay, well, how does calculus help you? Well, what is very special about this point right up here? Well, it's the top of a hill. Right? Now, if you're walking up a hill, right, what happens when you get to the top? You kind of level out, right? You're on top, and now I'm standing, and I'm flat, basically. And then when I go down the hill, I'm like this. Well, remember, the derivative is telling you the slope of these tangent lines. Right? So it's telling you what angle, effectively, you're going up. And when I get up to the top, boom, and I'm flat, right, the angle of that line, right, should be 0. It should be a flat line. So if I draw the tangent line up here, it should be flat. Okay? That's supposed to be flat. So what I'm looking for is when is the derivative, when is the derivative? Well, what's the derivative of this line?
0.
It's 0. When is the derivative? 0. So this is how calculus ends up getting used, is you plot your function, and then you need to decide where are these maximum points, or possibly where are minimum points. And you do that by finding the derivative and figuring out where it's equal to 0. So for instance, in pre-calculus, or maybe even in Algebra 2, you might have looked at a parabola and figured out where its vertex was. Right? And they give you some formula for how to do that. And the formula, whatever it is, tells you how to plot in the coefficients, right? If, say f of x equals ax squared plus bx plus c. And they say, okay, use these coefficients, you can find the vertex. And the vertex of a parabola, say it's upside down like this. The vertex is exactly the maximum point on that parabola. Right? If this was a parabola, that'd be the vertex. Well, calculus says you don't have to memorize those formulas. Right? We just take the derivative. Okay, the derivative of this is going to be, well, let's see, the a is a constant, you don't worry about it. Derivative of x squared is 2x times a. So 2ax. Okay, plus, okay, the derivative of x was 1 times b. And the derivative of a constant is 0. So that's the derivative. We want to know where it's 0. So we set it equal to 0. So let's see, we subtract b. And then we divide by 2a. And if you remember, that's actually the x-coordinate of the vertex of a parabola. That's the formula, negative b over 2a. Right? You don't have to memorize it anymore. You can just use calculus. You can figure it out if you want to. Right? And of course, you can find the y-coordinate just by plugging this back into this this equation here. So this is how we're going to use it a lot. We're going to be able to answer all sorts of weird questions that come down to translating some real-world problem into calculus. You know, you have a ladder sliding against a wall at a certain rate. You know, you're going to be able to figure out at what speed it's falling when it gets down to here. All these things all are going to come from calculus. Another thing which I won't get into today, but they're just formulas just like these. Sometimes you have inverse functions. Right? So recall, if you have the sine function, you might have the inverse sine function, right? Also known as arcsine. Okay. You need to come up with derivatives of these things. Okay. We're going to also talk about something called hyperbolic functions. These are really kind of cute. Some textbooks don't do them a lot of justice, including the two I chose, but that's not a real problem. There's something called the hyperbolic sign, which is minus, kind of a strange looking function. And the motivation for this isn't clear. I mean, why in the world is this related even to the sine function? And why are these e's in here? But if you ever took a class in complex analysis, it becomes immediately obvious. There's the hyperbolic cosine, which is given the same way, just with a plus. Right? And of course, I've given you all the tools that you need to actually find the derivatives of these things. So once you have the definitions, you can find the derivatives. And the cool thing, and one of the motivations for the naming, is the derivative of hyperbolic sine is hyperbolic cosine. And that shouldn't be so much of a surprise. When you take this derivative, that minus is going to come down and turn that into a plus, and everything else is going to stay the same. Okay, so that's the hyperbolic stuff. Let's see. I think if I forget anything on here. Yeah, I mean, we talked about already that you have a position function, you have a velocity function, you have acceleration function. Right? Velocity is the first derivative. Acceleration is the first derivative of velocity, but it's also the second derivative of position. Second derivative just means you do it twice. All right, third derivative means you do it 3 times. Okay. Leave anything out? Okay, so I don't really want to talk about that. The last thing that we may get to in this course, it just depends on how the time works, is anti-differentiation. So anti-differentiation is just doing differentiation backwards. Right? What do I mean? Well, let's say I told you what my velocity function was, and you wanted to write down the position function. That's what anti-differentiation is supposed to help you with. Now, it's a little bit more tricky because you have to go backwards, and you run into some problems. Here's the first problem. Anti-differentiation. Let's say I start with a velocity function, 2t. Okay. What is my position function? T squared, that's the answer, right? Is this correct? What about t squared plus 1?
Plus c.
I hear plus c, okay. So, what do I mean? What does he mean by plus c? What do you mean?
Any constant.
Any constant, okay? I can put anything here. When I take the derivative of t squared, I get 2t. Plus some constant, it always goes away, right? Derivative of constant is 0. So I could actually put any constant here. Okay, so we would say that the antiderivative of 2t is t squared plus c. Okay, but it's a little bit worse than that until you prove something. How do I know that this is the only function whose derivative is 2t? I mean, clearly there's not just one, right? Of course, there's infinitely many as I let c go. But how do I know there isn't some weird function I could concoct that after I took the derivative and I sorted everything out, there'd be a lot of cancellation, and I'd end up with 2t at the end? The answer is, well, without proving something, you can't know that. But it does turn out that these will be the only possible antiderivatives. Right? So it's very nice. It's exactly what you would hope for up to this plus c. Right? And a lot of times what you can say, if you want to be brief, is you can say that the antiderivative is t squared up to a constant. Plus c. You don't, plus c kind of sounds pedestrian. Plus c. I'm so high school. Plus c. So you say up to a constant, or modulo a constant. That's what you say. All right. This will be the transition period into 166 at the end. Because what 166 is all about is answering a different question, which is if I draw a curve. All right? So again, I started with a nice curve, and I picked a point, and I drew a tangent line. Well, let's say instead that I pick 2 points on here, and I want to know how much area is under this curve, right, between these 2 points. Okay, again, this is a very hard question. Okay. But it's going to turn out to be intimately related to the question of finding a derivative. In fact, it's just going to be, you have to, well, there's more to it, but you're going to have to compute an antiderivative. So it turns out that the question of what is the slope of this tangent line and what is the area under this curve are intimately related. Okay. And this, of course, is where Math 166 will start. And that's what that'll all be about. But here's the beauty. The whole year, right? Calc 1, Calc 2, all you're doing is answering 2 questions. Slope of this tangent line, area under the curve. 2 questions. And this term, we only have 1 question. Slope of the tangent line. That's it. So does this seem that bad? You just have a... There's some stuff that we're going to get into that I didn't talk about today that's a little more clever. But as far as actually working the math, it's just following some rules. Right? And none of the rules are super, super complicated. Okay, now, as promised, I have the pre-final. This has got basically all the material from the course in it. And you should go home and try to work it, bring it back on Tuesday. It'll be due by 4 o'clock on Tuesday. I'll tell you where. Have fun with it. Do your best. We'll see how the results turn out.
Does the homework that you gave us due tomorrow?
No. Homework. So this is not counted as homework. Okay. Homework is always due the following Friday. All right. And I wrote on the homework when it's due. I mean, it should be on there.
We do have class Monday, right?
Okay, so we're 160.
Yeah, 2:30.
Yes, 2:30 to 3:45. So on Monday, we will have a recitation in Archer 185. That's where we can look at homework problems. We won't do the pre-final problems, but I really want you to work on that by yourself. So the pre-final stuff, do this by yourself. Don't work. I know I said I wanted you to work together. Not on this. Think of it as an exam, but as a take-home exam. Okay? Okay, if you do not have a copy of the syllabus yet, or the problem set, I have a few extra. All the material that I've handed out is all available on the webpage. Typically, I don't want to print them all out, so I won't, but the first week, while you're getting settled, I will. A few people have emailed me with questions. That's perfect. I love it. Colin had asked me about typing up homework. As you probably noticed, I sent out an email giving you some resources. At least there's links on my webpage now to resources. It actually won't be that hard. I made up a template. So that all you have to do is install the software in your system, copy in the template, and then you can pretty much fill in the stuff. And it'll be a lot cooler than writing it up. All right. Well, then I guess I'll see you guys on Monday.